Hello, everybody. Welcome to this contributed talk for QCrypt 2020, which is about efficient simulation of random states and random unitaries. This is a joint work with Gorjan, Alagic, and Alexander Russell. Here's an overview over our results. We study the simulation of random quantum objects, so that is random quantum states and random unitary operations. In this context, we develop a theory of stateful simulation. So that would be an analog of the so-called lazy sampling technique. For random states, we can achieve such a simulation efficiently. And for random unitaries, we at least prove that such a simulation is possible in polynomial space. Finally, as an application, we design a quantum money scheme that is unconditionally unforgeable and also untraceable, which is kind of an additional privacy preservation property. Let me start with an introduction. As most of you might know, randomness is extremely useful, and that's not only for cryptography, but also for applications like Monte Carlo simulation, more generally for randomized algorithms, etc., etc. But of course, randomness is also expensive. So we would like to cut some corners every now and then when we supply the randomness for our applications. We give an example. That's the most simple example of just a random n-bit string. Here, we can, of course, actually exactly and efficiently generate such a string if we have the model of randomized computation, so if we have random bits at our disposal. And of course, the randomness cost of such a generation is n bits because we're generating an n-bit string. This is, of course, the ideal object that we generate, so this is indistinguishable from the ideal object by definition. We can, however, simulate such a random n-bit string using less than n bits of randomness if we only want to do this in a way that's indistinguishable from a random string to a limited distinguisher. And this is what's achieved by a pseudorandom generator. In this case, we have a security parameter lambda, and the randomness cost is just polynomial in this security parameter, independent of n. And this pseudorandom string that is produced in that way is indistinguishable from a random string to any distinguisher that has a runtime that's polynomial in the security parameter lambda as well. Let's move to another example, and that's the one of a random function. So here we look at a function from m bits to n bits, such that each output of this function, f of x, is picked uniformly and independently at random from the set of n-bit strings. What we want to do is we want to solve the so-called oracle simulation problem. We are supposed to supply some oracle that is indistinguishable to some distinguisher from an oracle for such a uniformly random function. One way to solve it is, of course, to pick such a uniformly random function, but that's very expensive because we have to pick a uniformly random output for each input. So the cost is n times 2 to the m bits of randomness, which is prohibitive for many applications. And note that the runtime and the memory cost of such a simulation will actually be larger than the randomness cost. Luckily, we can cut some corners in many cases. So for example, if we know that the distinguisher will not make more than t queries for some constant t, then we can solve this oracle simulation using the so-called t-wise independent functional family. And this can be done with a randomness that's proportional to t times n. So the number of queries times the number of bits of output. In a different regime, we can again use the idea of pseudorandomness. For some security parameter lambda, we can sample a function from a function family using an amount of randomness polynomial in lambda. And this will then be indistinguishable from a uniformly random function if the distinguisher has a runtime that's polynomial in that same security parameter lambda. Finally, we can achieve exact simulation if we give up the idea that our simulation is supposed to be stateless. So there's the lazy sampling technique, which just amounts to sampling the outputs of f whenever they are needed. And this is, of course, stateful because we have to note down the outputs for later use if we get asked the same input twice. But it's exact and it's efficient. At least it's polynomial time in the number of output bits and the number of queries that a distinguisher ends up making. Note that there's a difference between the query limited case, because there, in the case of t-wise independent functions, we really need an a priori bound on the number of queries, where here we just have the guarantee that no matter how many queries are made, the simulation runs in polynomial time in that number. Before moving to the simulation of random quantum primitives, let me briefly illustrate with a few examples how far-reaching the applications of the contents of this table are. So first of all, T-wise independent functions can be used to, for example, construct information theoretically secure message authentication codes. Pseudorandom functions are extremely important, essentially in all of computationally secure symmetric key cryptography. They can be used to construct, for example, computationally secure many-time message authentication codes, but also for CPA secure encryption, etc., etc. Finally, lazy sampling is extremely important, for example, for proving security in the random oracle model. As an example, it's, for example, used to prove indifferentiability of domain extension schemes like the Merkle-Damgard or sponge constructions. Now let's move to quantum states and quantum operations. Let's quickly recall what these are. So quantum state is just a unit vector in a complex vector space. So we can think of it as an element of the sphere in that vector space. More precisely, it's actually an element of the projective space because the phase of that vector doesn't matter, but that's not extremely important for this talk. The most fundamental kind of operations in quantum theory are, of course, unitary operations. And these are mathematically expressed as unitary matrices from the 2 to the n times 2 to the n matrices. And the set of such unitary matrices forms a compact Lie group. Both of these sets are extremely nice, mathematically speaking. And because of their compactness and additional properties, they have a natural notion of a uniform distribution, which is called the Haar measure. Let me give an example application of Haar random states. Of course, you all are familiar with the no cloning principle, which states that quantum information cannot be copied. And one of the oldest ideas of quantum information processing, and I guess the oldest idea in quantum crypto, is let's make money from this. So here's how to make a money scheme from a Haar random state. This is from an idea by G, Liu, and Song from 2019. We just have the bank pick a single Haar random state, phi, and now for all eternity, whenever asked to hand out a bill, it will just produce a copy of this state phi. Verification, of course, works by measuring whether purported bill is actually equal to the state phi or is orthogonal to it. This money scheme is unforgeable because of the no cloning principle, which holds in a very strong sense for Haar random states. And it's also untraceable because all bills are the same. So when the bank receives a valid bill, it cannot infer anything about its transaction history. The question is, of course, can the bank sample such a random state? And as you can probably guess, sampling such a random state exactly is impossible. So let's look into this. This brings us to the main part of this talk, where I want to describe our results about simulating random quantum objects. Let's begin with the Haar random state. So what we want to simulate is such a Haar random state picked from the Haar measure on the 2 to the n dimensional sphere or projective space. And we also view this as an oracle simulation problem. So the oracle we want to simulate is an oracle with trivial input, and whenever it's invoked, it outputs a copy of a fixed Haar random state, phi. Let's first look at exact sampling. This is completely infeasible because we are looking at a state drawn from a continuous probability measure. So that requires an infinite amount of randomness measured in bits. The first naive idea for resolution of this problem is to just discretize the sphere. Turns out that the sphere is very big, so a discretized version of it is still very large in the sense that it requires a huge amount of randomness to sample a random point on the discretized sphere. Also, note that such a discretization will automatically imply a query limit because somehow as you supply more and more copies of quantum states, they become more distinguishable. We'll have a look at this later in more detail. Luckily, we can actually efficiently simulate a Haar random state in certain situations. So for example, in the query limited case that we've looked at before, a so-called state T design suffices. So that's a family of quantum states where sampling a random element from this family only costs a polynomial amount of randomness in the number of qubits, and the query limit is T, and this random sample from the family is indistinguishable from a Haar random state as long as we only supply T copies at most. Recently, G, Liu, and Song have also introduced the concept of a pseudorandom quantum state, which is kind of the analog of a pseudorandom function, for quantum states. So this really works exactly like a pseudorandom function. So you have a state family where sampling a random element from this family only costs a polynomial amount of randomness in some security parameter lambda. And the sample is indistinguishable from a Haar random state as long as the distinguisher has a runtime that's limited by a polynomial in this security parameter lambda as well. One of our main results is that we can supply the last line of this table, which is an analog of lazy sampling for Haar random quantum states. So we devise an efficient but stateful simulation algorithm that can simulate this oracle that outputs copies of a Haar random state efficiently in the number of qubits and the number of queries that the distinguisher makes. Let's have a look at the case of Haar random unitaries. The first two lines of the corresponding table look very much the same as for Haar random states. Exact sampling is infeasible, and while, of course, discretization brings down the randomness cost from infinity to some finite amount, it still requires an infeasible amount of randomness, and it implies a query limit. In the query limited case, however, there is a possibility of simulating efficiently, and this is given by unitary T designs that many of you might know. So this again is a family of unitary matrices where sampling a random element from this family costs only polynomial amount of randomness in the number of qubits the unitary acts on and the query limit T. And this is indistinguishable from a Haar random unitary, at least approximately, if no more than T queries are made to this unitary. Let's move on to the pseudorandom setting. Here, the situation is not quite satisfactory at this point. This is because while pseudorandom unitaries have been defined by G, Liu, and Song as well, at this point, there's no provably secure construction known. Again, we can contribute by supplying the last line of this table, at least in some form. We prove that it is possible to perform a stateful simulation of a Haar random unitary against unbounded distinguishers using polynomial space. Unfortunately, we cannot give a concrete algorithm that performs this, and we can also not prove that this is possible using only polynomial time. So we can only prove a space-efficient simulation is possible. Let us come back to the application of harmony. When introducing harmony a couple of slides ago, we asked the question, can the bank actually sample such a random quantum state? The answer is, of course, no, but they can simulate it, as we have seen in the last couple of slides. So one solution was already given in the work by G, Liu, and Song, where they use a pseudorandom quantum state family to create a computationally secure, untraceable quantum money scheme. Our new approach now allows us to construct a quantum money scheme that uses stateful simulation and thereby produces an unconditionally secure, untraceable quantum money scheme. So here we really have unconditional unforgeability, so money cannot be copied, and also unconditional untraceability. Let me use the next couple of minutes to explain why the stateful approach to simulation of Haar random quantum states is actually necessary. To understand this, let us have a look at a stateless simulation scheme for Haar random quantum states. And such a scheme works by picking a random element from a finite family of quantum states, phi k here, and then outputting copies of this fixed quantum state phi k. So in some sense, this kind of simulation is very similar to the ideal object where a random state is picked according to the Haar measure in the beginning for initialization, and then copies of this fixed state are output. There's a problem, however, and that is that two quantum states, no matter how close they are, become near perfectly distinguishable as soon as enough copies of them are supplied. This kind of extends to quantum states that are sampled according to different probability measures on the set of quantum states. So in particular, if I have on the one hand a Haar random state, and on the other hand I have a state sampled from this finite state family that specifies my stateless simulation scheme, then these two become distinguishable as soon as I supply enough copies of my sample. Therefore, this implies that any stateless simulation scheme or one could also say any pseudo-random quantum state, any state T design, of course, but any kind of stateless method for simulating a Haar random quantum state necessarily has a limit on the number of queries attached to it that a distinguisher is allowed to make before it becomes distinguishable from an actual Haar random quantum state. And a similar argument can, of course, be made for random unitaries. In the last part of the talk, I'd like to tell you a little bit about the techniques that we use to achieve our results. First of all, we used the ubiquitous technique of purifying a mixed quantum state. So what we're striving to do is simulating a random quantum state, in this case, a Haar random quantum state, right? So one way to do this is to just provide a part of an entangled state is set. So in pictures, we have this entangled state, it's a pure state, it's deterministic, then of course one of its subsystem looks like a random state, and that's exactly what we want to simulate. So in fact, stateful oracle simulation is possible without any randomness, strictly speaking, just by maintaining entanglement with the distinguisher. But what do L copies of a Haar random state actually look like to the distinguisher? So what kind of mixed quantum state do we want to simulate? From representation theory, we know that L copies of a Haar random state actually look like the normalized projector onto the so-called symmetric subspace of the L-fold copy of the local Hilbert space. Here's a summary of the two facts we've seen on the last slide. L copies of a Haar random state of a d-dimensional quantum system look like a maximally mixed state on the symmetric subspace of L copies of CD. But this also looks like half of a maximally entangled state of two copies of that symmetric subspace. From this observation, we kind of derive the following simulation strategy. We maintain a maximally entangled state of two copies of that symmetric subspace between the distinguisher and the stateful simulation algorithm. And now if the distinguisher makes a query, we apply an isometry to extend that maximally entangled state from L to L+1 copies, but by only acting on the part that is with us, with the stateful simulation algorithm. So maybe this is best explained in pictures. So here we have a distinguisher and a stateful simulation algorithm, and they both have a couple of quantum systems. And these quantum systems are in fact in this maximally entangled state of two copies of the symmetric subspace of the local system. So basically, if you take the symmetric subspace of all the blue system and the symmetric subspace of all the yellow systems, then they are in a maximally entangled state. Now, if the distinguisher makes a query, we apply an isometry to the blue systems to create two more systems, a blue one and a yellow one. And then we reply to the query with the yellow system. And this has the effect that now we have still a maximally entangled state of two symmetric subspaces, just that these symmetric subspaces are of one more copy, actually. Let me use the last couple of minutes to describe the nitty-gritty technical contributions that we made to realize the stateful simulation protocol that I have described to you in the last couple of slides. Most of the work went into actually implementing the isometry that extends this maximally entangled state of two symmetric subspaces to such a maximal entangled state, but of symmetric subspaces of a larger size. To this end, we developed several new algorithmic tools for quantum state preparation without garbage. So what does that mean? We devised algorithms that as an input get a classical description of a quantum state, but this is supplied as a quantum state itself, this is a classical description. And then they basically attach the quantum state that's described in the classical description to it. So the input is just some description, and the output is that description tensor the quantum state without any additional garbage states. This is important because now such an algorithm can actually be run in superposition, right? I can supply a superposition of descriptions, and then the output will be a superposition of pairs, description, and the state. And this is important for implementing this isometry. Using these routines for garbageless quantum state preparation, we devise a concrete algorithm that can implement this extension of this maximally entangled state on two symmetric subspaces by an additional copy. The result for random unitary, on the other hand, uses completely different techniques. So there we combine several nice ingredients to prove that it is possible to perform a stateful simulation of a Haar random unitary oracle in polynomial space. Firstly, we apply exact unitary designs that have been proven to exist but have not been constructed to devise a stateful simulation algorithm that we can prove works for a distinguisher that makes parallel queries. So that means they have a quantum state that has many subsystems, and then they query each of these subsystems. But you know, they never take the output from an oracle and feed it back into it. Subsequently, we can prove that this same algorithm, stateful simulation algorithm, actually also works against adaptive distinguishers. And we prove this via a post-selection kind of argument. So this is basically via probabilistic teleportation. What we do is we basically perform non-adaptive queries, but then we do this with halves of maximally entangled states, and we just you know, teleport in the input and hope that the Pauli correction of teleportation is the identity. If that's the case, we proceed, otherwise we abort. And because everything else is exact, even with this small post-selection probability, we still get an exact result. Finally, we also utilize the uniqueness property of the Steinspring dilation. That is that if I have two Steinspring dilations of the same quantum channel, then they are related via an isometry on the dilating system. Therefore, if we perform all operations coherently, so we use you know, Steinspring dilations of all operations, or we delay all measurements, etc., we don't use any classical randomness, then if we find ourselves at some point having answered T queries using an exact T design, there's no regret. Somehow, it would seem like we cannot answer another query, but that's not true, because we can just take our register, the register of our stateful simulation algorithm, which is in fact a Steinspring dilating register of the T-fold twirling channel with the Haar random unitary, and transform it into the one that would have resulted from a different Steinspring dilation of the T-fold Haar twirling channel that uses a T+1 design. And all of a sudden, we can answer another query. This brings me to the end of my talk, so let me summarize. We have developed a theory of stateful simulation for Haar random quantum primitives, that is, Haar random quantum states and Haar random unitaries. In the state case, we have presented an efficient algorithm for approximately performing stateful simulation of a Haar random quantum state. And in the case of unitaries, we have at least been able to show that it's possible to perform such a stateful simulation actually exactly, but only in a space-efficient manner. And we don't know anything about time complexity. Finally, we have also presented an application of the Haar random state simulator to devise an unconditionally secure and untraceable quantum money scheme. There are also a couple of open questions, naturally. One of them is the most straightforward one, and that is, can we efficiently simulate random unitaries in this kind of stateful and unconditionally secure way? Another one is kind of inherited from Jilu and Song 19, which is you know, the table that I showed about simulating Haar random unitaries had another gap, right? Which is the one of pseudorandom unitaries. So by now we have several candidate pseudorandom unitary schemes, but none of them is proven secure. So this is something that we should do in the future. Thank you very much for watching.